Um, so I am John Horvosnik. Who am I? I am a name that is not as familiar as all the ones that have gone before us in the chats today. I've been working with Postgres for the past 20 years or so, with PostGIS for 9 or 10 years, 15 years with government experience, which is where I started doing map stuff with the Department of Labor, some for GSA, some for National Geospatial Intelligence Agency, DoD, et cetera, et cetera, et cetera. I've been at Crunchy Data now for the past 4 years, supporting various projects across the entire Postgres sphere, a lot of them touching PostGIS. Postgres and PostGIS. This is a quick and easy slide. You are here at PostGIS, Virtual PostGIS Day, which means you probably know what that is or have interest enough in it to understand what it is. And hopefully that you understand that it runs on Postgres. These two generally work in concert for all of your GIS needs. It's very happy, it's very cool. And most of the other talks have pointed to that in some way. What you might not be aware of or might not use as much is pgRouting. pgRouting is an extension that's built on top of PostGIS. It lets you route networks of nodes and vertices together to create queries that create maps, network graphs, viability graphs, least distance, things like that. It is built on all the stability that you're used to in Postgres and PostGIS. It allows you to do things dynamically by using Postgres functionality. And these are some of the functionalities that it allows you to do, all those things I just said. There's some path finding, some point-to-point finding, driving distances. One of the interesting things is that while PostGIS is a requirement for the extension, you can use the extension non-spatially, which means that you can find and create network graphs, minimum spanning trees, and that sort of data without it being geographically tied. I have other talks on that too, but they're not relevant here. A little more specific to pgRouting. This is what pgRouting looks like, and these are the terminologies we're going to be talking about. There's a lot of setup to this entire presentation for the actual substance. I'm going at it that you may not know what you're looking at or talking about. The image on the right here shows us a little fake town. We have houses, a ballpark, some business centers, some vacant lots. All of those blue dots at the intersections are what are known as vertices and nodes. In these instances, we're counting them with a physical lat-long position. They are a physical location on the map. The lines between them are streets or lines or edges or ways. They are the connectivity between two vertices or nodes. You'll also notice that next to each one of those is a number. The number is the cost associated with each one of those lines or edges. When you connect those lines and edges together, you're creating a path or a route. And that is what's happening when the house we're using a query here that says, find us the shortest distance from this house in the top left down to this building down here in the bottom right. And it traverses the graph, finds the shortest path by the lowest number of sums of these costs. So that's a vague, high-level view of what you're trying to do with pgRouting. In actuality, we're going to play with this for half a second just to show you what it looks like in the real world. We're importing data from Boston. And it's as easy as these 6 commands. 5 of these commands are setting up the data and getting it viewable. Well, 4 of these commands are setting up the data. 2 of them are making it so that we can view it in the Crunchy PG tile serve. That's all you need to do with it. OSM has data up there on a live DVD that already has Boston in there, which is why I chose that. It's nice and easy. You can try this at home. This is an image, so you will not be able to copy and paste this, which is kind of mean, but good luck. Thank you. This is what the data looks like when it's imported. It's basically 2 tables. There's a bunch of other sequences, IDs, primary keys, et cetera, associated with it. But looking at these 2 tables, our left-hand side is our table of dots. Those are the vertices. If we go back 2 slides, it would be the intersections. And the right-hand side is ways. It's the table of lines. You'll notice that there's metadata associated with each one. The ways table tells you whether each one of those ways is one way. It has I'm looking for it in there, it has a tag ID in there. The tag ID tells you in OSM whether it's a highway, a street, a pathway, a bike lane, something like that. This is useful because what that means is we can limit our graph to only highways, only bikeways, only things that are potentially available to a specific use case. This comes up useful in the next two slides, well, next three. This one shows what this data actually looks like. The left-hand side is what the Waze vertices looks like. That is 15,000 or so records of dots of intersections of all the intersections of two ways in Boston. And the right-hand side shows you the road network. There are 20,883 of those. I would have thought it would have been a little bit larger considering the 15,000 intersections. I would think it might be closer to 3 or 4 times that, not just an extra 5,000, but these are the numbers we got out of it. Here's what a query looks like. This is, and the query on the right-hand side we'll go into a little bit deeper a little later in a different way, but this is using the pgR algorithm to create the best route between 2 points. So we picked the point by the O in Boston is the closest vertex to the Sam Adams statue in downtown Boston. The left-hand side is where we're going to, which is a building I picked on MIT's campus, but I can't remember which one. So let's just go with it. It's going over there. What the query is doing is saying, select this information from the function with an inner query that then has the source and destination. Those are just nodes. They are not positional data. And we'll talk about that a little later too. What's interesting with this is, and if I knew Boston at all, I could tell you what bridge that is, but I don't. We can now say, hey, what if there's construction on that bridge or that bridge is closed for a reason? And we can easily get a new query by just adding the where clause where the GID is not in the 2 nodes that we know are on top of the bridge. And all of a sudden we have a completely different route to get to the same point. Now, this is using the same start and stop point. So it's fundamentally the same query, but we change the graph that we're looking at. So the information we get out of it is different. So what we want to do is we want to take that information and use it on the ocean. This sees a lot of things. It's why it's used as a metaphor in everything. It's big, it's scary, and that's no different with mapping it out. Why would we want to do it? The impractical reasons are pretty well stated. Because I'm bored, because it sounds like a project, because I said so. And most importantly, the ocean has no roads, so it doesn't have any strict paths to get from point A to point B. The practical reasons include that same idea. It has no roads. So since it has no roads, we kind of want to create a network that we can look at to try to determine where we're going, how we're getting there. We can also use it to create better dynamic predictions. If we have a node network, we can use it to look at historical pathing and see where shipping lanes are, what's avoided generally, where weather patterns disturb different things differently. We can kind of generate that on the fly over time. The the right-hand side over here shows you right now the old way and the new way of doing it. If I have a ship and I want to know the radius it can travel from where it is right now, that is 1,000 kilometers from the center. That's a circle that says, hey, I can reach anything around here. The right-hand side is using the pgRouting nodes that I've made to do the same thing. And you can see that the intelligence on that is different. By using the pgRouting graph, I no longer am considering the fact that I could get to any of the Jamaican ports or Georgia and South Carolina up there on the right-hand side. And might even slowly take out some of these Yucatan ports out here. So it does add a lot of extra information to what you're doing and how you're doing it. But how do we get there? This is where it gets a little more interesting. All of the projection people, all of the actual GIS people are going to curse at me for this, but I am using a very dumb, simple way to do this. This is very much the crawl of the crawl, walk, run phase. We are creating a grid of the entire world at different resolutions. This resolution is 1 degree of separation. So this internal query here that is bolded is using the generate series function in Postgres to create 180 by 90, the entire world gridded off. Then we're going to make sure that we don't have any dots that are on land. And we're going to create an ID and make a point out of this information. And this is what this ends up looking like. Now that we have those dots, we can connect those dots. And you'll notice that's the background on my screen right now as well. But this is all of the dots. If we look at the query over here, again, with the row number as ID, we're making a line where the points are within, I did 1.9 because it's less than 2 away from things. Basically, this gives us the diagonals. You could say 1.5, 1.6, 1.7. Because this is in the 4326 coordinates, we're dealing in degrees. We know that the diagonal is going to be somewhere around there, and one from ladder long directs. What gets interesting here is you'll notice that there are lines that cross over land, like these lines over Cuba. These are obviously not correct pathing routes. Interestingly, down here, you also have them in Costa Rica and Panama. And I'm pointing that out because the next slide does the next 2 things to fix that. Number 1 is we delete anything that is going over top of land. And you can see that, hey, all the Bahamas are a little bit better. We have a little bit more movement around there that looks correct. We don't have any lines that are going over Cuba. And then we add back in the valid ones. One of the things about node and network graphing is you could try to do it dynamically, but there's always going to be some extra information, either by knowledge, by information, or by subject matter experts that say, hey, we know this is here. There's no dots in the actual Panama Canal at 1 degree of separation because it's a random dot. So we're just connecting these 2 dots on our own, and I cheated. I just know what the connecting node numbers were and the max ID number in the table just to make sure that we had no collision. So I just reconnected those back out with each other. One of the things you will notice with this graph is it looks like there's only one path to get around the horn of Florida, the end of Florida. There's only one. This looks like a very heavy bottleneck. We know that not to be the case, but that's because we're doing things at 1 degree of resolution. So the way we can fix that is to look at things at different degrees of resolution. This is 1 degree, and we're zooming in on Key West because you're just talking about that area of Florida, and also because it shows you very easily what the difference is in between distances. Each one of these lines, 1 degree, that line, that box, then translates into 10 boxes on this 0.1 degree, and 0.01, 10 boxes on this 0.01 degree. The math mostly lines up for the multiplicative factors of how much bigger they are from each other. The edge distances, as again, the projection people will say, and Paul said earlier, this is good for near the equator. It is not good for anywhere else because we are doing things in degrees. For our cases and for our purposes of just illustrating things, it's good enough for me. But what you'll also notice is that at 1 degree, this line is 111 kilometers or so across. This is the type of information we see. At 0.1, it's 11 kilometers, and at 0.01, each one is around 1 kilometer. So we're starting to get a little close to street detail, and maybe the type of movement that you would see out of a ship. I mean, we don't think a ship's necessarily going to lean on an entire line for a full 111 kilometers. Now that we have our network, what do we do? This is where pgRouting comes in. pgRouting has a number of different functions and a number of different classes of functions and a number of different algorithms in each class of functions. What I like about pgRouting is that I don't have to be smart to use it. I don't have to know how to implement a pgR Dijkstra, the Dijkstra algorithm, or the A-star algorithm, or the 4 different ways it's doing an all pairs comparison. But it gives you the functionality if you have your data and your network set up to do those on your own. A lot of these are concepts that you may have touched in computer science or may not have if you haven't touched computer science. The traveling salesperson is one that most people know. I'm on a route, I have to hit these 10 places. What's the easiest way and shortest way to do that? Without overlap, with overlap, bidirectionally, single directionally. So there's a lot of different functional things and decisions that you can make on here. All pairs algorithms are comparing all of the pairs of all the nodes in the network graph to produce some level of cost calculation, biggest, smallest, minimum trees, things like that for your information. Spanning trees are creating a forest or a tree that has the minimum number of minimum number of edges necessary to connect all the vertices possible. So you'll get a lot of dead ends. You'll get a lot of reuses. You won't get a lot of reuse of edges. You'll get single paths down, which ends up being more a quote unquote forest than a network that way. The ones we're going to take a deeper look at are the point-to-point and driving distance algorithms. Now there's a few different queries for each of those, but we're going to continue looking at the Dijkstra algorithm for the shortest path, and we're just going to look at the generic driving distance for the driving distance algorithms. So the point-to-point algorithm is letting you pick 2 points on a map and going through your network for the best possible route for them. This is showing you up in British Columbia, Victoria to, the words are chopped off and I don't know Canada well, so some island up there and some port that was nearby there that showed an interesting shape where it's actually navigating around different islands. The driving distance calculation is the same one we did before, where we're providing it a threshold, and that threshold is 1,000 kilometers, and it's telling us how far out on every line it can get before it runs out of that threshold. So this is where it gets interesting again, because you see the circle. The circle is if you just draw a straight radius 1,000 kilometer circle and go for it. The routing network gives you a path that says, hey, it's obviously not the full circle. So it gives you a little bit more of a full idea of what's possible. I've also previously had you could take this information and create like a rubber band hull around it to provide a better version of that circle, but the level of effort to do that is a little high on the service for something that I think looks a little cooler with those colors. So what does the query actually look like? We saw what the pictures look like. So how are we getting there? This is what a pgR Dijkstra query looks like with some callouts. Number one, we're calling the function. This function takes 3 parameters. The first parameter is a query. Excuse me. The query is generating the network that we're going to be using. In this case, we're saying get everything from this table as the query. It requires specific callouts and names returned. Because it's looking for an ID, a source, a target, a cost, and the geom. Actually, I don't remember if it is looking for the geom. I don't believe it is. That's probably wrong. But the ID, source, target, and cost have to be explicitly named that way. So generally, what ends up happening is you end up renaming your query columns to fit that field. The beginning and the end are node numbers. It's taking in the node ID that are the source and target that are inside of that inner query, and that's what it's using as its route. And then that's about it. I'm joining back against the paths table here at the bottom so that my external query is getting the geometries that are associated with this, because it does not return a geometry. It is a set returning function, which means it's returning a table or multiple records. The inner query, like I said, needs those explicit column names. The beginning IDs beginning and ends are not positional information. That's all good stuff to know, because we can then see what an actual query looks like. And this is a little bit more of a monster. We still have that internal query. You can pull it apart by looking at those single quotes around it. But we don't want to consider our entire table, because our entire table is, as we saw in those previous slides, very large. At 0.01 degrees of fidelity, of resolution, it's 355 gigabytes large. If we did that, we'd crash our Postgres server. I've done it before. But if you limit it, because you know that, hey, you're only going to be looking at, hey, maybe, and what I'm doing is I'm creating a line between the 2 points and then buffering it by buffering the envelope of it by 5 degrees. This is useful because my route isn't going to be a straight line. My route might need to circumnavigate an island or a peninsula or something else. So it needs to go a little further out than just what a straight line would do. So this is internal is doing that. The other call outs out here, rel ID as ID, because my column name isn't the same, I need to change it. And I don't have a cost associated with my table. So I am creating a cost table on the fly and just using the length of each of those line segments as the cost. And lastly, because I'm looking for an ID over here, what I want to do is I want to use the k nearest neighbor algorithm, and this is what this operator down here is, to pick the closest point to the one that I know is a physical point. So here are my lat longs, putting it in the right reference system, and then getting the geometry from it where that's the point, and then getting the source ID from that and providing that as that information. It says source twice. That's perfectly fine in this case, because I know that my grid points and my grid paths points are going to be fine with that, because they're interchangeable. They're both designed from the same place. This is what that looks like. This is actually what that explicit query looks like. This is creating a point-to-point at 1 degree fidelity that is navigating around part of Mexico, down towards Belize. And you'll notice that because I rejoined it back with the geometry, I have the line segment, which is what's being used to draw this out here. I can also look at the costs here and say, hey, it's 1.4, 1.4, 1, 1, 1, 1, 1.4, and know that that means that, hey, this is in order. These are the first 2 diagonal points that are out. Then we've got the 3 straight points, 1 diagonal, and down. That's just the general math of it's not 1 degree direct. That means it's not a straight line. It's a diagonal. This is what it looks like when you do a driving distance query. You'll notice that in general, it's similar. We have, ignore my select star in bad form up there, but that's there. We have a pgr driving distance function. We have in quotes the inner query, and our inner query is doing a lot more this time, because this time we want to limit it to by specifically a distance. So I'm taking the beginning point that I have, this lat long here. I'm buffering it by 1,000 kilometers, 1 million meters. Well, I'm turning it into a geography. I'm buffering it by 1,000 kilometers, and then I'm turning it back into a geometry. This lets me continue working in geometry space for everything else I'm doing, so that it actually works with everything, but do the calculations on the distance as a metric distance. Everything else in here is what you expect, what you saw before. I'm getting the ID, source, target. I'm doing the length as a cost. I'm not actually asking for the geometry back here because it doesn't use it. Here's the KNN to find the original node. And this is the cost threshold, which is 1,000 kilometers. And for driving distances, these 2 numbers are very easy to keep in line, because if I know that my driving distance isn't going to be longer than this, I don't have to search a network that's further than that distance out from my original point. That's also why our length, our cost length, is done as casting to a geography, because these will add up to be less than 1,000 kilometers. And this is what this query looks like. It returns a lot more line segments. We have 182 of them, but it's still in the same ballpark on size and how it works. And this is what it looks like down in the bottom right-hand corner. You'll see you can't go over continents, you can't do any of that. But it gives us another good idea of where everything is. And again, it's color coordinated, so we know at a glance what one's nice to look for. This is the color coordination is not actually part of pgRouting. That's just the visualization layer. So don't make any assumptions that it's that magic. But I mean, it's as simple as doing a I'm just doing an array calculation to see what set it fits in based on what percentage it is of the final line there. There's much more visually aware people that could probably do cooler gradients there, but it's kind of neat as it is. So what's next? Those are the two things we've looked at. And from where we're standing, they're very uninformed. There's not a lot of that extra information that we talked about up in the beginning. So right now we have a static graph. It takes up a lot of disk space. At 0.01 degree, it's half a terabyte. That includes both of the indexes, the sequence, there is no sequence, 2 indexes and the entire table. The entire table is 355 megabytes large. The edges have no real cost associated with them. Our costs are only their distances. So there's no way for us to weight a preference of any sort of information saying, hey, more people did go here, less people did go there. It's also a one-sized grid. Now we have 3 of them, so we have 3 one-sized grids, but if you ever look at a road network, when you look at a highway, your highway segments are measured in quarter of miles. When you look at a street segment is measured in feet or meters, because edge to edge, it's a lot smaller before you get to a vertex. On a highway, it's a lot longer before you get to another exit or a place to make a decision. That's not to say all of them are done that way, but in general, you can use dynamics, the wrong word. You can use graphs that are spaced separately to save on cost savings, let you know where things are supposed to be, preferred routes that you know, hey, it's always going to go that direction, et cetera, et cetera. So there's some benefit to having some mixed use graphs on that. Where we want to get to is an informed graph. This is a picture of AIS data of ships in British Columbia, US border area, where we've snapped them to our 0.01 grid that we have. The two things that does is, one, we can see at a glance where all the ships are going, how they're going there. And 2, we don't have all of those extra grid spaces that were created but not being used. There's a lot of blank space out there that isn't blue, which means that there's a lot of grid that we created that hasn't had a ship on it. Now that's a little unfair because this is only 1 day's worth of data, but it's 1 day's worth of data. For those that are interested, AIS is the Autonomous Identification System, I believe. It's a requirement that all ships over a certain gross tonnage have an antenna that self-identifies themselves and pings. So it's something that is publicly available data. It might not be easy to find publicly available data, but NOAA and the U.S. Coast Guard has it for certain historical periods and going back at least the past decade. So this is only 1 day's worth of data, but we can use this to inform our graph and say, hey, these are the preferred routes or routes that happen often. We can also use that information to do the other things that are over here. We can identify routes that we didn't even think about. Points like this that are actually going so far inland that didn't fit in our graph because they didn't fit neatly into our grid. Things like that would help. We can also use live data as opposed to historical data to improve our graph. Now, this isn't something I got into the database, but this is a screenshot of Hurricane Iota from earlier in the week and its wind trajectory over the past week. Using this data, we can turn off those graphs just like we turned off the bridge in Boston and say, no, you don't need to go here. Stay away from here. So that's something that can happen. and something that would be beneficial to it. We can also use charts. If we're going to map the ocean, we might as well use the map of the ocean. This would let us actually route around buoys, route through channels, navigate shoals, shallows, reefs, anything like that, and keep that information pertinent to your navigation. What's more interesting with that too is you can dynamically change that based on what type of vessel you are. You're not allowed in these protected waters. You are allowed in these protected waters. You have a sailboat, you're fine. You're on an aircraft carrier, you're not. So we can actually expand or shrink our graph based on that, the same way we were looking at our Boston data by putting a tag on it and saying, hey, this tag is bike friendly. We would say, hey, this tag is motorboat friendly, which would keep the heavier vehicles out of that area, but the singular boats in. The other thing we can do is we can do dynamic generation. We don't need to store 0.5 terabyte of data at a time just to use it in the Gulf of Mexico. When we need to or want to, we can create this whenever we want. This query is a mess because everything had to be embedded inside that internal query in order to make it, but it does work. This is providing a route point between, and again, I just picked some random points so that I knew I could have over 200 nodes and pick node 1 and node 200 and say, hey, make a graph. But it does work. Some more intelligence can go into this to make it a little bit bigger, a little bit smarter, but that's where that is. And honestly, that's about all I got. These are the links for everything that we did use. A big thank you to OpenStreetMap, to Noah for all the places I got the data, pgTileServe for making things easy, et cetera, et cetera, et cetera. I'll have this uploaded too for all of that. I also do have this system up live, so we could do a live demo or we can do a live demo and questions, whatever is best, whatever works best. Steve, you got any ideas?
You have still 10 minutes left in your talk.
Cool.
So you can do some demos, but we do have some questions that you want to.
Yeah, let's do both. I'll ask the questions. I'll bring up the webpage.
Okay. So this is a long one, but the question actually is short, but there's a lot of preface to it. Christian says, I love pgRouting. Thanks for the talk. One issue that I think must be super common in routing from in 2 locations that are in the middle of edges, right? So on a road network, if they haven't put a node at every single house,
right,
on a route from one house to another, you have, so what he says is, the usual solution that I see in tutorials is simply to use the closest node, but that might not be optimal in a lot of situations, especially in road or utility networks. I have come up with my own solution that creates temp tables, splits edges, and creates new nodes using pgRouting, join back to the temp table, then drop the temp table, but it seems pretty tedious for such a common use case. Am I missing something more out of the box? I realize this is a bit touch off topic from the seafaring example, but I thought I'd ask since that was touched on early in the talk. So
what I've done, and it's not perfect, but you can use it sometimes, is instead of my k-nearest neighbor finding the closest node, I know my point, and I have my network, I can dynamically add to that network with a quick union on the table. So what I'll do is I'll find the point that I have, find the closest edge to it, and then I will do, and someone else will have to help me here, but I can't remember the specific PostGIS queries, but I'll do st closest point, I think that's it, which will give me the closest point to that edge. Then I'll split that edge on that st closest point, and then I can create 2 nodes so that instead of being in the middle of the node, I'm in an L. So I go from that node to that new point I created, from that new point I created to that other new point I created. So you're basically dynamically adding 4 nodes to your node graph. It's a little trickier in practice, and it might even be tricky to say, but that's one of the things and one of the ways to do it.
Okay. Did that make sense, Christian? You can put an answer in or something like that, or in the chat. While we're waiting to see if Christian, yep, he said thanks.
So
right. The next question, John. this is very cool. How about, and actually both Graham, I think that's pronounced Graham, and Philip have basically the same suggestion. How about building a grid that has greater density near shore, but lower density in the open seas?
That is part of the point of doing that. Yes, absolutely. That's one of the things that comes up with the idea that what I was trying to say at the end. One of the ways you can do it, make it smarter, is exactly what you said. Because you're getting all of the travel down here, and that's actually a good thing here. You can see this is, here we go. This is the base grid. That's what a driving distance is. This is 1,000 kilometers, and it's kind of hilarious that it draws one thing faster than the other, so it gets like that. But that's how quickly you can do this at one degree of separation. Once you start zooming in, I have it so that it automatically picks a different degree of separation for each one, which it doesn't seem to actually be doing right now. But yeah, I don't know why it's not doing that. Oh well, it was earlier. Likewise, we could do the Dijkstra distances, and actually, here's a great example that I love showing. The reason we buffer it is because if I want to say I want to go from here to here, I get nothing back because my network isn't connected because I'm not traveling all the way around Spain. So, but if I go from here to here, this is what my buffer does. It allows it to go from there to there. I'm buffering by 5 degrees, so 5 degrees is shorter than the entire distance of Spain. These are all the ports, but that's what a Dijkstra does. When you're in the open sea, it's pretty easy. And just to show you it routing around some, not working there because we're too far away, it will work there. So this is where it becomes a touch and go on what you need, what you want to see, how big it needs to be, et cetera, et cetera. I was able to, while people were talking, actually make the AIS-based data. So this is what the AIS-based data looks like as a grid. And this is where it gets real interesting because I picked 2 points going from Jacksonville to Savannah here. And you can see that it isn't necessarily the closest distance because my historical ships go a little further out to sea because they can go a little faster, as opposed to staying closer inland. And that's true of quite a few places. It also makes it difficult because there's things that you think are obvious, like, hey, I should get a pretty good driving distance from here, but there's nothing within the appropriate distance to get to that ship to create a driving distance. New Orleans is fun. Anywhere near here. This is what a driving distance looks like with the historical ship data. If I were to start here and I'm trying to go 1,000 kilometers, these are all the locations I can get to based on what other historical ships have done recently. Likewise, and to the other questions, this is where it gets interesting because cutting close to the coast is how you get more fine data because that's where most ships are. If I pull the entire grid, it's actually too much data, but you would see that actually in TileServe, I believe I have it. This is the AIS data as it is in the entire grid. As you zoom in, you can see that this historical data starts at ports and spreads out. Seems pretty obvious. I believe that's most of what I have. So if there's any more questions, Steve?
Yeah, I got it. Oh, here's one from Frederick. Wouldn't it be relevant to use constrained Delani triangulation with additional internal points?
It might be if I knew what that meant. This is where I am not a PostGIS or maritime expert. This is something that I came onto as a, hey, honestly, the reason this happened was because of this example here. We're going around Cuba, right? We can tell that this is an island. If I want to say, can I get to this port on the other side of Cuba? It's pretty easy in Postgres to say, okay, get me the closest distance to this island, draw a hull around the island, tell me the distance around the hull, and I can say, okay, best case scenario I can. But because PostGIS stores everything as a polygon, if I then was doing that on Central America here, Panama is treated as an island. So it's not, if I said, hey, can I get to this port? It's not as easy as saying no, because I would have to connect all of these together and create a complicated polygon to say, all right, where's the distance where it fails? And that was what my point in the slide that was saying continents are big, islands are small. Like, at what point do I stop creating all these coastlines and mixing them together to say, no, you can't do this anymore?
Okay, so just for future reference, Delani triangulation is the way you can tessellate a surface rather than it's a triangulated irregular network. So then rather than building a grid, you take the points and you make triangles out of all the points. And so I think what Frederick is saying, throw additional points in there and you'll get an interesting grid that would give you some of the lines and stuff.
Yeah, I'm excited to play with that. I'm also excited to play with, and that's the thing, you can make your grid out of whatever the heck you want to make it more reasonable. I mean, this is definitely just an easiest case scenario where we're just using a square grid because we can generate series in two different ways and play with it pretty easily.
Yeah,
I'm excited to play with 3.1 and the hexagons to see that as well.
Right. I mean, I think the other, as you said, this is just like the beginnings of how do I even approach this problem. It's not the authoritative way that you would do shipping, right? Especially after once you show the charts, right? Because this still wouldn't work for things like I have an aircraft carrier and there's a bridge going across this inlet. You're not going in, right? So
right. Here's the Savannah to Jacksonville from here. Does it actually work? Is hugging the coastline compared to when we saw it with the historical difference. So yeah, there's the getting a little closer to walking.
Yeah. There is a verbal question from Noor. I'll see if he's actually, or she is, still wants to ask. Noor, you can unmute yourself if you'd like to talk. Noor Alabasi. I guess Noor no longer needs to ask the question. So hold on, let me lower the hand.
They're showing Panama Canal too, just to say you can route through things like that.
Right. Okay, so there's not a question, but a reply from an anonymous attendee to the question Christian gave, which is also similar to what, because Christian said he basically does what you do, what you suggested. And the anonymous attendee says, pgRouting has a solution for this, which is exactly what John outlined, adding virtual nodes. You can dynamically add the cost from the points to the virtual node if you want to have the highest accuracy. And he said, see the with points function family. And then he gives a link to the doc for that. And I'll put that in both the general chat and in the Discord chat. So if people want to take a look at that. And then Evan also gave another pgRouting practical guide written by our own speaker today, Regina again. So I'll put that in the chat as well.
Yeah, the end result here is pgRouting is cool. Do not be afraid to play with it because it's pretty easy to set up networks. It's pretty easy to also crash things because if you get greedy, it uses every little bit of RAM you have until it takes everything down. So do it on a test system, but do play with it because it's easy to get into.
So I have, I think your talk also did an interesting thing of pointing out what is actually the biggest problem for pgRouting, which is not pgRouting's problem, which is the availability of network data, right? So that's, I think, what like when I've done this before, the only thing I ran into was like, well, I can use OpenStreetMap data, but they don't have speed limits for most of the roads, right? And I don't know if they do bridges or not. They might do bridges, like, so you can't, like, you know, when a bridge goes over a road, you can't actually walk off the bridge down to the road down below or drive off the bridge. I don't know if they do overpassing and stuff like, and I don't know if pgRouting can take advantage of that.
pgRouting does because it's just the networks between them. So each one of those things has to be informed by something. So if you have two lines that cross over each other, but there's no vertice at where those two lines cross, that's assumed to be an overpass.
Right.
Or a bike lane or something that can't actually interact with the other road.
Okay, so that's cool. But still, OpenStreetMap data basically is good enough for walking. I mean, I know there was some company that tried to use OpenStreetMap data for routing. I don't know how far they got with that, but I don't know.
It's pretty good, but you have to know what you're doing with it. I mean, it's not like Apple Maps in its infancy where it's going to tell you to like walk into a building or something like that. But you have to know what the ways, vertices, what the types and tags are. But it's a trial and error method. It definitely is.
And again, it still comes down to the quality of the data underneath. Like
right.
the Dijkstra algorithm is pretty well known. The software does it the way it's supposed to do it. The hardest part that I've found is actually coming up with data that's ready to go into it.
Yes,
that is what I
absolutely. Yeah, and that's the problem with this project is informing that data, is trying to figure out how to make it something more than just like these are connected.
Okay, so Raul points out you can use OSM to pgRouting tool also by Regina to import OSM data into PostgreSQL, and all the data and routing constraints will be imported also. So that's good to know about. I will put that in the chat as well.
Yep, that is how those Boston examples were created. That's pulling data down from a live OSM DVD and just running the OSM to pgRouting.
And given that Regina lives in the Boston area, that is exactly why we see Boston as most of the examples for that stuff. But okay, so thanks a lot. I think that does it for all the, let me just make sure there's no new questions. Hold on, while I was doing this, where are the questions? There's all these windows I have open. Okay, yeah, there's no new questions. All right, thanks a lot.
Yeah, thank you very much. Thanks all.
Okay.